What makes the sun shine? What is the source of solar energy? How does sun produce its energy? It turns out that it cannot be a chemical burning, like burning of coal. A more technical term for chemical burning is oxidation. It turns out that the sun, with all this mass of 10 to the 20 kilograms or 300 times the mass of the Earth, if it was ordinary chemical burning, the sun would have burned out in a few thousand years. And yet we know that it has been shining for about 4.6 billion years. And there are different pieces of information that point to that number. One is that we have fossils here on Earth that are several billion years old, 3 billion years old or so. So the sun had to shine for at least that long to provide enough heat and energy for the life to be sustained on Earth. So it cannot be chemical burning. It turns out that the process through which sun makes the energy is fusion, nuclear fusion of hydrogen into helium. The particular mechanism that is operating in the case of the sun is called proton-proton chain. And it turns out that it's effective in stars like our sun, maybe a few times more massive than our sun. In very massive stars, there is a different mechanism, so-called CNO cycle, or for carbon, nitrogen, and oxygen cycle. But for this fusion to start, the temperature of the core must be at least 10 million degrees. Why is that? Well, two protons, they both carry positive charge, right? And as charged particles of same charge, they actually repel each other. So to bring them close enough so that the strong nuclear force can actually bind them, I have to send them in at very high speeds. So they repel each other, but if they are moving fast enough, they'll manage to come close enough to each other so that the strong nuclear force is going to bind them. High temperature measures just the average velocity of, or the average speed of the particles. There are three steps to the proton-proton chain. What happens in the first step of the proton-proton chain is that two protons form the nucleus of so-called deuterium, which consists of one proton and one neutron, with at the same time production of positron, which is a particle just like the electron, but instead of being negatively charged, it has positive charge. In every other respect, in terms of its mass, magnetic moment, so on and so forth, it's just like the electron. It just has the opposite charge. And there is another particle produced in the process. There are ghostly particles called neutrinos, which have practically no mass. For a long time, people thought that neutrinos have zero mass, but we've finally settled at a finite but extremely small mass. They carry no charge, and they have no magnetic properties. And because of that, they don't couple to ordinary matter like us. So these neutrinos that are produced in the sun's core, they just shoot through the sun, unhindered at all by the top layers. They move at the speed of light, and as we speak now, billions of those solar neutrinos pass through us every second, with us being totally unaware of that something is shooting through us. Why? Because they are ghostly particles. They interact weakly with ordinary matter, and therefore they don't influence us at all. In fact, they shoot through the Earth. They enter on one side, right, if the sun is up, and they exit on the other side, the probability of them interacting with atoms of ordinary matter is really, really low. So they form deuterium, 2 protons. This process is very slow because what needs to happen, not only that you bring 2 protons close, but the proton has to actually transform into the neutron. So 2 things have to happen. The proton has to transform into neutron, and they have to be close enough. So the probability of that is rather low. On average, it's 1 such event per 14 billion years, the age of the universe. So you can say, well, how come it happens at all? Well, keep in mind that the mass of the sun is huge, 10 to the 20 kilograms. And 3/4 of that mass is hydrogen. Therefore, there are many, many, many protons there. So although the probability of 2 of them fusing to form the nucleus of deuterium is low, the supply of the protons is high enough so that indeed we get a lot of these reactions every second. Now, what happens is that this positron and the electron that is present around somewhere, right, because the sun is electrically neutral, will actually annihilate each other and form gamma rays. In the next step, the nucleus of deuterium fuses with another proton into the nucleus. So this is the nucleus of deuterium, D, heavy hydrogen. Deuterium fuses with another proton into the nucleus of helium-3, an isotope of helium, and then 2 nuclei of helium-3. This process is relatively quick. Fuse to form the nucleus of helium-4 with the release of 2 protons. So look what has happened. I have altogether, I need 1, 2, 3 protons to form 1 nucleus of helium-3. I have 2 such nuclei fusing together, so 6 protons have gone into forming these 2. Then I end up with nucleus of helium-4, helium-4, with the release back of 2 protons. So I've used 6 protons, return back 2. So effectively, when everything is said and done, 4 protons have been fused into the nucleus of helium-4. And the energy is released because the mass of helium-4 is slightly less, by a fraction of a percent, than the mass of 4 protons that went into making up the nucleus of helium-4. And that missing mass has actually been converted into the energy via famous Einstein's relation. So I have 2 protons fuse and give me the nucleus of deuterium. They also give me a positron, neutrino, and energy. And this stage, fusion of 2 protons into deuterium, is the slowest part. Okay? Then I get this nucleus of deuterium fusing with another proton to give me the nucleus of helium-3. It's an isotope of helium. Just like ordinary helium-4, it has 2 protons in the nucleus, but only 1 neutron. So therefore, it's lighter, right? And I also get energy out. Again, because it turns out that the mass of the helium-3 nucleus is slightly less than the combined masses of the deuterium and proton nuclei, and that difference in energy, a difference in mass, has been released as energy. And the last part is that I have 2 such nuclei of helium-3 fusing into the nucleus of helium-4, and I get back 2 protons plus energy. Energy, of course, is in form of gamma rays. So what has happened is, as I mentioned before, 4 protons, the net result is that the 4 protons have been transformed into the nucleus of helium-4. Which has smaller mass than the combined mass of these 4 protons. Okay, so what happened to that missing mass? Well, it has been transformed into energy at every stage. So, and thanks to Einstein's special theory of relativity, we know how much. You're familiar with the famous Einstein relation E equals to mc squared. If m is mass difference, it has been transformed into energy E that is related to that mass difference precisely by this relation. And this is, of course, speed of light. So we know exactly what fuels the sun, what kind of mechanism is responsible for this energy production in the sun.